Hello, in this video we will derive the conservation of momentum. Again, we use a three steps cooking recipe, and first we define the control volume. So the control volume is the volume where we calculate on the momentum, and the next thing is that we define the momentum itself. So the momentum is the product of the mass and the velocity, and in the local representation it's the product of the mass density and the fluid velocity of the particle, and the integral over it is the momentum. Now momentum is conserved somehow, and the rate of change of momentum, which is equal to the forces F acting on the control volume, is more or less Newton's law, that we have the change of the momentum, the total change of the momentum equals the forces. So from classical mechanics, the mass times the acceleration equals the forces, and this is more or less what is written here. So based on this definition, the question is, what are the forces? The forces on the right hand side. The forces are the sum of surface forces acting on the body, like we have here some attraction and some pressure acting on the body itself, and then we have some forces due to momentum of the molecules, which is also entering the forces there, and then we have some external forces which are volume forces, like the gravity or the electromagnetic forces. And these all forces are summed up and are then represented in this right hand side of the equation, which will change the momentum. And this is how the momentum is conserved, because usually these forces are kind of from an external momentum itself, and so it conserves the momentum itself. Based on the definitions of the forces, we then additionally need the third ingredient, which is the Reynolds transport theorem, which derives the left hand side of this equation. So before we looked at the forces on the right hand side of the equation, and now we look at the left hand side of the equation. The left hand side of the equation will be transformed by the Reynolds transport theorem. Having all these three ingredients together, we can derive the conservation of momentum in this formulation down here, and there we see how the left hand side is transformed by the Reynolds transport theorem from this quantity to that, and the forces are simply inserted in a local representation, and that's basically it. We have derived now the conservation of momentum, and if we would introduce for this bluish term here a Newtonian fluid, we would arrive at the Navier-Stokes equation. So we can conclude that the conservation of momentum plus the Newtonian fluid will give us the Navier-Stokes equation. This is a key message I would like to give you from the conservation of momentum, and the next step will be that we derive the conservation of energy. Thank you.